Hello, I'm Janusz Holowaty from West Pomeranian University of Technology in Szczecin, Poland. Together with my co-author Bernard Wichtowski, we prepare an article about technological cracks in welded joints of railway bridges in service. Of course, the railway bridges are located in Poland. Layout, introduction, quality of welds in railway bridges, stress concentration, fatigue test on butt welds, stresses in welds with cracks, and summary. While verifying the quality of welded joints in railway bridges in Poland, it was found that many of them contain cracks of technological, fracture, and fatigue origin. This problem is associated with early welded bridge structures in which many technological imperfections were discovered. A testing result on approximately 200 bridges in service are given. The tests were carried out over the period 1967-1990. The number of joints tested was nearly 16,000, and the number of cracks discovered in the joint was nearly 440 in the 34 bridges tested. The first diagram is showing the number of bridges and welded joints which were tested. The bridges were grouped according to the year of construction. The first welded railway bridge in Poland was constructed in 1936, so this is the first period up to 1940. 8 bridges were tested. In 7 bridges from that period, cracks were discovered in the welds. Next period, this is the period after the Second World War, when many bridges were replaced and many new welded bridges were constructed. From that period, 48 railway bridges were tested, and in 18 bridges, cracks were found. Looking further for further periods, it appears that the quality of welds was improved, and from the 1960s, the cracks in welds were only found occasionally. The second diagram is showing the bridges and joints with cracks, with hot cracks, technological cracks. For the first period from 1936, 7 bridges were tested with cracks, so this is over 87% of total number of bridges, because 8 bridges were tested from that period. The number of joints with cracks was 124, so it is nearly 18% of the total number of welded joints which were tested. The situation for the period after the Second World War also, many bridges were constructed with poor quality of welds. In 18 bridges, the technological cracks were discovered, so it means in 37% of the bridges tested, the cracks appear. Total number of cracked joints for that period is 270. All the cracks discovered appear during welding when there is no service load stresses. Connection between stress concentration and crack initiation is a fundamental feature of the fatigue. Crack proliferation depends on loading and the member shape as well as its size. The larger the component, the lower stress increase, and it is easier to maintain crack proliferation. The problem of steel structure fatigue strength as well as initiation and proliferation of brittle cracks is widely given in the literature. However, there has been neither a physical theory able to describe fatigue effects quantitatively, nor a homological theory which can formulate all their mechanisms. For durability assessment of bridges with cracks in welded joints, the most useful seems to be an analysis of the behavior of a long-term operation along with results obtained from laboratory tests of analogous specimens. Strength and aging are particularly dangerous if they appear in areas where stress is concentrated. It means around a welding imperfection, in welds and heat-affected zones. The largest stress concentrations are caused by flat imperfection, including longitudinal cracks. So concentration of stresses is very large, and the theory of notch stresses should be applied. This is an example of the basic meaning of such formulas. The question of the fatigue strength for particular joint structural solution tests were carried out on the model specimen, which are marked A, B, C. I described the specimen later. Fatigue tests were carried out for pulsating tension with frequency 5 Hz and stress ratio 0.1 according to the standard requirements. In total, 60 specimens on 7 load levels were tested. Fatigue test result on butt welds. 3 types of samples were used in the test. The sample mark A, it means sound welds of good quality. Fatigue limit was estimated 125 megapascal. Specimen B, welds with internal cracks. Fatigue limit was estimated nearly 90 megapascal. And C, welds covered by one-sided rhomboidal cover plates. Fatigue limit was estimated nearly 80 megapascal. So such a solution with rhomboidal cover plates were used in early layaway bridges to strengthen the butt joint, which is here. It was the intention, but it is evident that using cover plate on the welded flange joints lowers the fatigue strength to a large degree than internal cracks in the welds. So the fatigue strength is lower than for welds with cracks. Each time cracks appeared in the flange material at the edge of the cover plates, independently on the quality level of the butt welds. An attempt to explain the lack of growth in existing cracks or initiation of new cracks under service in dynamically loaded structure was undertaken. The visibility and reliability of this structure may result from the fact that they have not been under conditions which are necessary for failure initiation. The influence of different factors necessary for non-developing fatigue crack initiation was assessed. Many different hypotheses resulted from laboratory tests were taken into account. An analysis was undertaken on 4 selected bridges located on 3 railway lines. 2 of these bridges were constructed in the years 1938-1939, with the other 2 in 1947. So it was the period where the quality of butt welds was not so good. In total, 10 X-ray examinations of butt welds with cracks were carried out over 5-year time intervals. Primarily, 776 X-rays were taken, on which 51 internal cracks were assessed. This is the table showing all the technical data of the 4 bridges. Of course, they were plate girder bridges. Number of girders is given. in the second column, of course with the guides which were tested in parentheses. X-rays which are executed. So for the first bridge there are 120 X-rays, and in parentheses number of cracks which were discovered. Of course, the stresses were also calculated for that load, for combination of actors with standard loading and with service loading. As you look for the stresses, they are not so high, so it was good for the structures. Analyzing the result, it appears that the service loads in the center line of the flange weight are 60 to 70% of the standard traffic loads. Each time they are lower than fatigue limit 79 megapascal determined from laboratory tests at the same load amplitude. Taking the log spectrum which was used in Great Britain according to the old standard BS 153, the value will be lower. It may be estimated that this spectrum allows the bridge lifetime to be 5 times. And summary, X-ray examination on the butt welds in main girders of railway bridges was carried out throughout Poland in the years 1953-1990. The examination revealed the unsatisfactory technical condition of welded joint in early welded structures. On 34 bridges, this is 22% of them, 437 welded joints with hot cracks were ascertained. Oh, this is nearly 3%. Repeated examination of the welds with cracks over 5 years intervals did not indicate any proliferation. An attempt to explain this phenomenon is given in the paper. And conclusion, in all the bridge butt splices, the calculated and measured stresses under service loading were not larger than the weld endurance limit for these joints. The numerical analysis and the fatigue test result confirmed the lack of crack growth. Hot cracking and other welding imperfection in structure joints are permissible if there is no further growth or reduction in resistance or rigidity. Thank you for your attention.